So, in today's lecture we will see what is called as Markov chains. And we will use Markov chains to design a randomized algorithm to solve 2-SAT. So, let us understand what are Markov chains. So, first we will see what is a stochastic process. So, a stochastic process is nothing but an indexed sequence of random variables. So, if you look at random variables x1, x2, so on, this is what is in general a stochastic process. So, we will write this as x. So, x is a stochastic process, we will write this as equal to x t, t belonging to some particular index set t. So, we will generally think of the small t as the time. Okay. So, we can think of, let us say, observing the number of cars which pass a given point at a given time t. Okay. So, we observe the vehicles passing and at integer times, time t equals 0, 1, 2 and so on, and the number of cars passing at a given point at a time t, that will be our random variable x t. Okay. So, these are stochastic process. We are interested in particular type of stochastic process. So, these random variables x1, x2 etc., there could be dependence amongst them. Okay. Suppose we know that certain thing has happened and the value of the random variable x5 is something that might tell us about tell us something about the random variable x6 or x7 and so on. But we are interested in just some very specific kind of random processes which will be called as Markov chains. Okay. So, what is the defining property of Markov chains? So, the probability that x t is equal to, let us say, a t given all the information up till time t. So, we know what are the values of the random variables x t minus 1. So, let us say this was equal to a t minus 1 and x t minus 2 equals a t minus 2 and x 0, let us say we start at time t equals 0, a 0. So, this probability is equal to probability that x t is equal to a t given x t minus 1 equals a t minus 1. So, this entire probability is equal to the probability that x t equals a t given x t minus 1 equals a t minus 1. So, in some sense the entire dependence on the other random variables is captured by the random variable x t minus 1. So, the probability that the random variable at time t takes a particular value given the entire history, the values that the other random variables, that is x 0 to x t minus 1, if their values or the history is known, okay, based on that if you try to compute the probability that x t equals a t, that is exactly same as probability that x t equals a t given x t minus 1 equals a t minus 1. These kind of stochastic processes are what we call as Markov chains. Okay. So, typically the values that this random variable takes, so x is a discrete random variable which means it can take, let us say, countably many values. So, let us look at this equation a little more carefully. So, the random variable x t can take countably many values. Let us say the values that it takes, we will call it as p0, p1, p n and so on. It could take infinitely many values, but countably infinite, and x t minus 1 could have taken values q0, q1, qn and so on. Now, the entire evolution of these random variables, so x t, the value of x t is equal to, let us say, p I. So, it takes one of these values. So, the probability that this is equal to p I given the entire history is said for Markov processes or Markov chains, this is going to be equal to probability that x t is equal to p I given x t minus 1 equals, let us say, p j. Okay. So, let us just try and capture this by means of a matrix. Okay. So, these are the on the rows there are these values p0, p1, pi, pi plus 1 and so on, could be an infinite matrix, and q0, qj so on are the values that x t minus 1 can take. Okay. So, what is the probability that x t is equal to p I given x t minus 1 is equal to, let us say, q j. Okay. So, we could just, so this is going to be this probability, let us say if we call this as, let us say, x I j. Okay. The probability that the random variable takes the value p I given that in the previous step or the previous random variable x t minus 1's value was q j, let us denote that probability by x I j. So, this matrix in some sense captures the information corresponding to how these random variables transition as time progresses. Okay. So, now this matrix a priori could be dependent on t. If it is not dependent on t, then those kind of stochastic processes we will call them as a homogeneous Markov chain. Okay. So, this matrix here captures the information corresponding to what is the probability that at the next stage the Markov process will be at a state p I given that at the previous step it was at q j. Okay. And if this matrix has no dependence on t, or in other words for all t's, if this matrix was the same matrix, those kind of Markov processes are what we call as time homogeneous Markov processes. Okay. And in this lecture and in this course we will bother only about time homogeneous Markov chains. So, time homogeneous Markov chains, they can essentially be represented by a matrix, we will call that as the transition probability matrix. So, the ijth entry of this matrix will denote the probability of x or a random process being in state j given that the process was in state I, let us say at time t. This is at time t plus 1. So, if at time t the Markov chain is in state I, at time t plus 1, what is the probability that the chain will be at state t plus 1? By the state of the chain, we mean the value that the random variable x I takes. Okay. So, let us see an example of a Markov chain. So, we can imagine a random walk on a graph. Okay. So, let us imagine this graph. Okay. These are the states 1, 2, 3, 4, 5, 6. So, there are 6 possible states that the random walk could be in. So, the random walk or the stochastic process x will be all consisting of all these random variables x t, where t belongs to natural numbers. Okay. So, x 5, for example, x 5 denotes the vertex the random walk is at during t equals 5. Okay. So, let us say you begin at this place, okay, at state 1 at time t equals 0, and then there are 2 outgoing edges, toss a coin and go to either state 2 or depending on the toss go to either 2 or 3. If you had gone to state 2, then at the next instance toss a coin and based on the toss 2 coins and based on whatever are the outcomes go to 1, 3, 4 or 5 and so on. So, keep on walking on this particular graph at any when you are at any particular vertex, look at the out degree and choose one of those vertices uniformly at random and move to that particular vertex. You can keep on doing this, and you keep on doing this, this can be used to define a sequence of random variables x1, x2, x10 and so on. Okay. So, x10 in particular will denote which is the vertex you are at time t equals 10. So, this is a Markov chain, and this is a Markov chain because it does not really matter. So, the probability that let us say x20 is equal to 3 given x19 is equal to let us say something alpha 19, x18 is equal to alpha 18 and so on. This probability does not really depend on the history by much. It only depends on which is the current state you are in. When you have reached let us say state 4, from here the transition is to one of states 2, 3 and 5, and that is not going to be dependent upon how you reached state 4. So, that probability, this transition probability depends only on the number of neighbors it has no dependence on how you reached 4. Okay. So, this entire thing, this entire random walk can be represented using a matrix. So, matrix, so this is the transition probability matrix, Pij is the, we will just write it as the probability of going from state I to j. Now, let us look at this a little more carefully. We can ask lot of questions when we have a Markov chain like that. We will think about only discrete Markov chains, and we will assume that the number of states are finite. Okay. So, when the number of states are finite, we can represent each of these states by a vertex of a graph and the edges denote whether you can transition from that particular state to some other state, and on these edges you can put these Pij. So, if you are at state I, Pij denotes the probability of going from state I to state j. So, the random walk on our graphs, we can think of that as a generic Markov chain. Now, we could ask this question: suppose we choose a state at random and continue walking for some fixed number of steps, say 100 steps. We could be at a variety of places, we could be at any of the vertices in this graph after 100 steps. What are the probabilities that you are at some particular state? So, we will denote that information by a probability vector. So, P is this vector where the components P1, P2, Pn denotes, Pi denotes the probability of being in the ith state. So, clearly summation over I Pi is going to be equal to 1. Okay, so, here when this we are abusing notation a little bit, this is the same matrix, this is we are using the letter P for the matrix and we are using small p for the vector, but here when we write Pij, there are two indices. When we write Pi, it just has one vertex, I mean has one index. Now, suppose instead of moving one step at a time, if we when we want to compute the two step probabilities, if you are at step I mean if you are at vertex I, what is the probability that you will reach vertex j in 2 steps? Okay. So, Pij denotes the probability that you will go from I to j in one step. That is, if you are already at j I, what is the probability that you will land up in j in the very next step? Let us denote by Pij2 the probability of going from I to j in 2 steps. In general, if we write Pm, this denotes a matrix whose ijth entry, so the ijth entry of this matrix should give us the probability that you will be at step vertex j given that you were at vertex I. So, this is after m steps. So, imagine that you are already at vertex I. In m steps, after m steps, when you look at the Markov chain, what is the probability that you will be at state j? Okay. Compute this for every I comma j, and the matrix that you get by placing these ij's, these probabilities is our matrix Pm. Okay. So, what should Pm be in terms of P? P is the matrix whose ijth entry gives us the probability of transitioning from state I to state j. So, Pm will be equal to P raised to m. In fact, Pm plus n will be equal to P raised to m times P raised to n. Okay. Why is this so? So, we will just verify that P raised to Pm, this is a matrix which we had defined earlier. this will be equal to p times p raised to m minus 1. Okay. So, let us say we were at state I and we need to reach state j in m steps. Okay. So, we could do this by choosing our first step, we will go to some particular vertex k and then from k we have to reach j. So, reach k in first step, from k reach j in m minus 1 steps, and this k could be any vertex or any state in the Markov chain. So, the probability of this is, so for a particular k this probability is going to be p I k times probability of going from k to j in m minus 1 steps, but that is going to be equal to p I k times, if you look at the matrix p raised to m minus 1, inside that the k jth entry essentially gives us this, and this is for one particular choice of k. The total probability is going to be sum over all values of k. So, k equals, say if you had n states, k equals 1 to n, this summation will give us the probability. So, this will be equal to p m I j, okay, and this is just p times p raised to m minus 1 in matrix form. Okay. So, this is going to be equal to, so this is what we wanted to show. So, let us see some worked out examples. So, let us say we had a Markov chain with 4 states. This happens with half probability and you go here with half probability. From here, let us say 1/3, you go back here with 1/3, go here with 1/3 probability. And from this, let us say you just go here and here, this happens with probability half, this happens with half, say this happens with 1/3 and this with probability 2/3. Okay. So, the transition probability matrix will be as follows: 1, 2, 3, 4 are the states, 1 to 1 0, 2 to 2 is 0, 3 to 3 is 0 and 3 to 3 is 2/3 and 4 to 4 is half. 2 to 1 is 1/3 and all these were 1/3. 1 to 2 is half, 1 to 4 is half, other is 0. 3 to 1 is 0, 3 to 2 is 1/3 and this is 0, and 4 to 1 is 0, 4 to 2, 4 to 3 is half. Okay. So, this is our transition probability matrix for this particular Markov chain. Now, if you want to look at 2-step transition probabilities, then, so let us just look at one particular example. If you wanted to go from 1 to, let us say 4 in 2 steps, you could either go from 1 to 4 and then stay at 4. That is one way. You go here and then stay here. The other way would have been go here and then go. So, these are the only two possibilities, and that will happen with probability. So, this happens with probability 1 by 2 into 1 by 2, and the other one happens with probability 1 by 2 times 1 by 3. If you had multiplied P with itself, okay, the 1 4 entry would essentially be 0 half 0 half multiplied with the 4th column. Okay. So, this will be multiplied with half 1 by 3 0 and half. So, that will give us 1/6 plus 1/4, that is the same here. Okay. Now, another thing is, if we start at one of the states, say P1, so this were our initial probability distribution on the states. So, each state, so let us say we were in state 1 with probability 1 by 4, state 2 with 1 by 4, state 3 with 1 by 4 and state 4, all these 4 states were equally likely. Then at the next stage, the probability that, so if you look at, if you indicate by Pt, the probability Pt1, Pt2, Ptn, let us say this denotes the probability that you are in state I at time t, then this is going to be equal to P0 times P raised to t. This is also, you can easily verify this. Now that we know some things about Markov chains, we will now discuss a problem which we can solve using these ideas. Okay. So, let me introduce what is called as a 2-sat expression. So, let x1, x2, xn be Boolean random variables, or sorry, Boolean variables. Okay. Now, you can combine these using disjunction and conjunction, okay, and we will combine it in the following way. So, let us say x I1 or x I2 and, so let us say x, so something x1 or x3 and x4 or x7 complemented and so on. Okay. So, expression of this kind will be called as a 2-sat expression. Formally, this will be AND of ORs, okay, or conjunction of disjunctions. So, this is also called as a 2CNF formula. Okay. So, more formally, we have clauses and each clause is a disjunction of literals, where a literal is xi or xi bar. Xi bar denotes the complement of it. Okay. So, you have an expression like this, and what we have is the, so if C1 is a clause, we have an expression of the form C1 and C2 and Cn. Okay. Now, what we are interested in is, so this can be thought of as a logical formula, and if you fix the values for x1, x2, x3 up to xn, this expression will have a true or false value. You can evaluate the expression. Okay. So, a 2-sat expression can be evaluated. We call a 2-sat expression satisfiable so let us say phi is satisfiable if there exists an assignment to the variables which makes the expression true. So, if you evaluate this particular Boolean expression, after plugging in the values of the variable, if you get 1 or if you get true, then you will say that that particular expression is satisfiable. So, our problem is we are given a 2-sat expression and we want to know whether the expression is satisfiable or not. Suppose this was our expression. If we put x1 equals 1, x2 equals 0 and x3 equals 1 or x3 equals 0, you can see that this expression will evaluate to. So, this will evaluate to 1, this will evaluate to 1 because x2 bar is 1 and this will also evaluate to 1. Okay. Whereas, if x2 was 1, then this will evaluate to 1, this expression will evaluate to 0 and this expression will evaluate to. So, this will evaluate to 0 and this will evaluate to 0. Okay. So, what we are interested in is, given a Boolean expression, a 2-sat Boolean expression, we want to know whether there is a satisfying assignment. This is an unsatisfying assignment, whereas if you had taken x1 equals 1, x2 equals 0, that is a satisfying assignment. So, does there exist a satisfying assignment? There is a deterministic polynomial time algorithm to solve this, but we will just see a randomized algorithm and we will convert, we will try and build a randomized algorithm for even 3-sat, where instead of 2 literals we will be having 3, we will look at clauses which has 3 literals. So, let us see what the algorithm is. So, the input is a 2-sat expression and the output is true if the expression phi is satisfiable and false otherwise. Okay. So, what are the steps of this algorithm? Okay. So, what we will do is very simple. We will just take a random clause. Okay. Initially, we will start with a random assignment. All the vertices or all the variables will be given, will be assigned true or false randomly. And then after that, what we will do is, we will look at these clauses. If any of the clauses is unsatisfied, you can see that that all the clauses need to be satisfied, because it is a conjunction. So, and of ORs. So, only if every clause is satisfied, the formula will be satisfied. So, we will pick one of the clauses which is unsatisfiable for a given assignment and then randomly change one of the literals in that to make that particular clause satisfiable, and then again recheck if the entire expression is satisfiable, and we will keep on repeating it for some number of times. Okay. When we keep on repeating it some number of times, we will say that if luck is on our side, we will get a satisfying assignment. Okay. In fact, what we will show is for every expression which is satisfiable, luck will be on our side. In other words, with a very high probability, we will come up with we will find out a satisfying assignment. So, we will begin as follows: choose a random assignment for the variables. So, let us call this as the initial assignment or A0, and then repeat the following steps. Okay. So, we will, while repeating, we will check unless a satisfying assignment has already been found. So, in between, if you find a satisfying assignment at any stage, you will quit, otherwise you will repeat these steps. The number of times, so we will write it as m times 2 times m times n square, where n is the number of variables. Choose a random clause, or choose any clause, does not have to be random, choose any clause which is that is not satisfied, change any variable to make that clause. Okay, and then if a satisfying assignment has been found, output true, else false. So, this is our algorithm. We will start by choosing a random assignment. After choosing a random assignment, we will evaluate the expression on this particular assignment. If the expression evaluates to true, then we will say that we will output that the expression is satisfiable. If even one of the clauses is unsatisfied, we will pick one of those unsatisfied clauses and change the variable inside that and see if we get a satisfying assignment. We will keep on doing this process for m 2 times m times n square. M is some parameter that we can fix later on. The higher the value of m, the higher the probability of success would be. So, success here would mean that if the given expression or the 2-sat expression was, if the 2CNF expression was satisfiable, then we would have to say satisfiable, and if it is not satisfiable, we should say not satisfiable or false. It is clear that this algorithm, whenever it is presented with an input which is not satisfiable, it is never going to find a satisfying assignment, and therefore, it is always going to give the correct answer, which is false. Okay, it will output false as the answer, and that is the correct answer. But when the expression is satisfiable, maybe there is a minor possibility, there is a small probability that we will never find out that satisfying assignment. We need to find the probability of such events. Okay, so, how do we analyze this algorithm? So, we will look at the following, we will analyze it in the following way. So, imagine any satisfying assignment. We need to bother only about CNF formula or 2 CNF formulas which were satisfiable, because unsatisfiable formulas, of course, we are not going to not going to make a mistake on that. So, if you have a satisfying formula, it could have many satisfying assignments, but we will compute the probability that it will find a particular satisfying assignment, and we will show that that probability itself is reasonable, it is reasonably high. Okay. So, let S be a satisfying assignment. We will compute the probability that our algorithm finds S. Of course, the algorithm may not find S, it might find some other satisfying assignment and quit, okay. But this probability certainly is going to be, I mean the probability that it will find this particular S, if we compute that probability, if that probability is high, that is good enough for us. Okay. So, we will introduce certain random variables. So, let us say A I will denote the assignment or the partial assignment at step I. So, here the algorithm keeps on modifying the random assignment, and at the ith step there is a certain number of I mean there is a certain assignment of values to the random to the variables of our expression. So, AI denotes that assignment, and let Xi will denote the number of variables in AI which agrees with S. So, S, let us say that is the following assignment x1, x2, xn 1 0 1 1 0, some binary string denoting the assignments to the variables x1 to xn, and A I is the assignment at some stage. So, 0 1 something. So, look at the number of, so look at each variable, and if those variables in the assignment, that is the current assignment in the algorithm, if it matches with S, then we will add 1. Then our, so if the ith variable matches, you can add 1, otherwise 0, and you sum it up overall. That sum at the ith stage, the number of variables which agrees with S at stage I, at step I, is denoted by Xi. So, now we want to compute certain probabilities. If you look at this random variable Xi, Xi initially is some number, let us say P, or let us say alpha, and then it keeps on increasing. It might even decrease at a certain stage, but we want to know what is the probability of it increasing. Now, if x, so x1, if you look at x1, x2, x, we will go on till mn 2mn square steps. So, this is a sequence. So, let us imagine that instead of 2mn square steps, we keep on going forever. Okay, we never stop. I mean, we stop only when we get a satisfying assignment. Okay. Now, or when we get this particular assignment S. Now, at any stage, if Xi is equal to, let us say k, after at the next stage what we do is, we had picked one random clause or one clause which is not satisfied by the current assignment and changed its value, when change the value. So, let us say we had picked a clause x5 or x6 bar. So, this is the clause that we picked at some stage. This is not satisfied by AI. So, AI does not satisfy this, and we flip the value of one of these x5 or x6 we choose randomly. Okay. So, this any variable to make the clause satisfiable. Okay. Now, since S is a, so this is an important point. So, this is the observation. Since S is a satisfying assignment, okay, if we call this clause as C, S satisfies C. Okay. But the assignment that we have is AI, and AI does not satisfy C, because C is one of those clauses which is currently unsatisfied. So, since AI does not satisfy C, at the next stage xi from, so xi's value can go from k to k plus 1. So, xi plus 1, so xi plus 1 can be equal to k plus 1 with probability greater than or equal to half. Okay. If we randomly choose one of the variables in this clause and flip it, xi is going to increase to k plus 1 with probability half. So, now we can compute this probability that xi is equal to k plus 1 given, sorry, xi plus 1 equals k plus 1 given xi equals k. Okay. Since we had taken an unsatisfied clause and flipped one of the variables in that clause, okay. So, there is a, I mean, one of these surely does not agree with S. Okay. It could be the case that both of them does not agree with S, but at least one of them does not agree with S. So, if we choose that randomly, we have at least half probability that in the resulting new assignments, the number of variables that agree with S is one more than whatever it was in the previous assignment. And therefore, we can write the probability that xi plus 1 is equal to ki minus 1 given xi equals k is going to be less than or equal to half. Okay. Since the probability of this probability is greater than half, the other probability is going to be less than half. Okay. So, does this behave like a Markov chain? Well, not really. If this was equal, then it would have been a Markov chain, but we can convert this into a, we can construct another Markov chain which behaves nicely. Okay. So, what we have here is probability that xi plus 1 is equal to k plus 1 given xi equals k is greater than or equal to half, and probability that xi plus 1 is equal to k minus 1 given xi equals k is less than half. Okay. So, we can think of this as a random process, not a Markov process, but a random process or a process or a random walk. So, from each step, if you are at step I, or let us say if the value is k, it goes to k plus 1 with probability half or more than half, and it goes back with probability less than half. Okay. So, less than half, greater than half. So, this particular random process has a tendency to move forward. What we are interested in is the following thing, xn. So, when does this, so if you look at this random process, when does the random process hit the value n? When does this random walk reach n? Okay. So, we need to, so if we call that as let us say a random variable z, Okay. We need to, so Z denotes the number of steps taken for the random walk to reach n. Okay. We need to compute expectation of Z. If expectation of Z is a reasonable number, if it is small, that means we will quickly find a satisfying assignment. When Z is equal to, when the random variable, when the random walk reaches the state n, it means that we have found an assignment which agrees with S, and S being a satisfying assignment, we have found a satisfying assignment. Okay. So, how do we compute this? What we will do is, instead of looking at this, we will look at the simpler random process, wherein from step 0 you go forward with probability 1, and from everything else go forward or backward with probability half each. Okay. So, now this is clearly a Markov chain. Okay. Maybe for the final state you can just stay there. Okay. So, there is no returning from the final state. So, if you look at this particular random walk, this random walk is surely slower than the, so let us call this as the random walk y and this is the random walk x. Y is surely slower than x, slower in the sense x has a tendency to move forward, because it takes the forward edge, or it goes forward from state k to k plus 1 with probability greater than half and comes back with probability less than half, less than or equal to half. So, now if you think of moving another parallel random walk such that the probabilities are half for both the forward edge and the backward edge, then clearly the random walk y is expected to be slower. There could be instances where y is faster than x, but in an expected sense x is going to always have a smaller the number of steps taken for x to reach, let us say, any particular state n is going to be smaller than the number of steps taken for y to reach the same step. So, the expected number of steps taken by the random walk y to reach the state n will be a bound, an upper bound on the number of steps, on the expected number of steps taken by the random process y, sorry, random process x. X being non-Markov, the analysis of the expectation is difficult, whereas y, by virtue of being a Markov process, we can compute this expectation quickly. So, let us just look at that particular computation. We will write this down as follows. So, we have a random walk, from 1 you go forward with probability 1, from 2 you come back half, go forward half, okay, and you continue this. Okay. So, this is the random process y, okay. And let us say z I will be the random variable. So, this denotes number of steps taken to reach n starting at 1, or let us call this as 0. Okay, so, starting at I. So, if you start from the state I, how much time does it take to reach step n? This could depend, this is a random variable, that random variable is what we call as Zi, and the expectation of Zi we will denote it by, so this we will call it to be Hi. So, Hi is defined to be the expected number of steps required to reach state n starting from state I. So, H0 is the quantity that is of importance to us in the algorithms analysis. If we show that H0 is less than some particular quantity, then our algorithm, I mean if we show that this is less than n square, then that means our algorithm has a chance to find the, I mean if you run the algorithm for n square steps, we expect to find a satisfying assignment. Okay. So, let us first compute the expectation of Zi. Okay. So, we can write this in by means of recurrence relations. So, H n is equal to 0, because if you start at the nth step, you immediately reach the nth step, you do not require any additional step. Now, Hi is going to be, by definition this is the expectation of Zi, this is equal to, at Zi you can with probability half, I mean if you start your random walk at the ith step, with probability half you can go forward and with probability half you can come back. So, Zi could be equal to 1 plus Zi plus 1 with probability half and 1 plus Zi minus 1 with probability half. Okay. Zi denotes the number of steps taken from the state I. If you had gone forward, then the total number of steps taken would be 1 plus Zi, and that happens with probability half. And if you had gone back, you would take Zi minus 1 steps, and that would happen with probability half. So, the expectation of Zi is half into expectation of 1 plus Zi plus 1 plus half into expectation of 1 plus Zi minus 1. Okay. So, this will be equal to Hi plus 1 plus Hi minus 1 by 2 plus 1. Okay. So, this is the recurrence that we can write, and H0 is certainly going to be 1 plus H1, because if you are at state 0 you straight away go to state 1. So, these are the recurrences. Now, we need to solve these recurrences and evaluate what is H0. So, this is what we will work with. H0 is equal to 1 plus H1, Hi is equal to Hi plus 1 plus Hi minus 1 by 2 plus 1, and Hn is equal to 0. So, this can be rewritten as H2 Hi minus Hi minus 1 minus 2 is equal to Hi plus 1. So, if we use this recurrence, we can write this entire system of recurrences as H1 is equal to H0 minus 1, H2 is equal to 2 times H1 minus H0 minus 2, Hi is equal to 2 times Hi minus 1 minus Hi minus 2 minus 2, and Hn is equal to 0. If you add these things, the LHS will add up to summation Hn. So, let us denote Sn is equal to summation Hn, n going from I going from 0 to n. Okay. So, this is Sn, this is equal to 2 times h 0 plus h 1 plus h n minus, let us say we will sum this up till, we will just sum this up till h I. So, this will be S I. So, S I is summation k equals 1 to 0 to I h k. So, this is S I, this is 2 times h 0 plus h 1 to h I minus h 0 minus 1 minus 2 times I minus 1. Okay. So, this we can write it as, oh sorry, there is an additional term that we have missed. So, these 2's sum to this, these sum to this much, and the other terms sum to minus h 0 plus h 1 to h I minus 2. Okay. So, we can write this as S I is equal to 2 times S I minus 1 minus S I minus 2 minus h 0 minus 1 minus 2 I minus 1. Okay. So, we can take one of these I minus 1 to the other side. So, we will get S I minus S I minus 1 is equal to S I minus 1 minus S I minus 2. Okay. So, when, so this summation there is a minus h 0 because we did not add the first term is not there. So, minus h 0 minus h 0 minus 1 minus 2 times I minus 1. So, S I minus S I minus 1 is going to be H I. So, this is H I, these terms cancel, is equal to H I minus 1, sum to I minus 1 minus sum to I minus 2 is H I minus 1 minus 2 times I minus 1 minus 1. Okay. So, H I plus 1 can be written as H I minus 2 I minus 1. Okay. So, this is the expression that we will use. Okay. So, now what is H? So, H n is equal to 0, H 0 is what we were interested, this is equal to H 1 plus 1, this is equal to H 1 is by this expression 2 times H 1 is equal to H 2 minus. So, in other words H I is equal to H I plus 1 plus 2 I plus 1. So, therefore, H 0 is equal to 1 plus H 1 and this is equal to 1 plus H 1, we can write it as 3. So, I here is 1, 3 plus H 2 and this is equal to 1 plus 3 plus 5 plus H 3, that is equal to 1 plus 3 plus 5 plus 7 plus H 4 and so on. So, this will give us 1 plus 3 plus 5 plus 7 plus up to 2 n minus 1 plus h n, and h n is 0, and this is equal to n square. So, we know that we can now conclude that h 0 is equal to n square. Okay. So, what this means is, if we had taken the random walk x, that would be going at a faster rate than y. Y itself will hit the state n in n square times. So, x is expected to, the expected time for x to reach the state n is going to be less than. So, expected number of steps for x to reach n is going to be less than n square. Okay. So, if we denote this expected number of steps by the random variable t, the expectation of t is going to be less than n square, and therefore, probability that t is greater than 2 n square is going to be less than half. This is Markov inequality. Okay. So, since t is greater than 2n, I mean the probability of t greater than 2n square is less than half. If we repeat it for mn square, 2 times mn square steps, and if we imagine all these steps, I mean these 2 mn square steps to be broken down into m blocks, each of size 2n square, in each of these blocks you have less than half, you have a less than half probability of not finding an assignment. So, the overall probability of failure is when all these m steps or m stages fail to find a satisfying assignment. That happens with probability less than 1 by 2 raised to m. Okay, that is an exponentially small probability. So, that concludes the algorithm and its analysis for the algorithm and the, so that concludes the 2-SAT algorithm and its analysis.